Hopefully in one video, we are going to discuss the entirety of the relevant parts of Chapter 5 for which to teach in the class. The objective of Chapter 5 is to do matrix operations on a given coefficient matrix to find eigenvalues. Obviously very, very valuable results for engineering linear systems. For aircraft, the eigenvalues can determine the stability of a system. I guess for most systems, eigenvalues come out to determine its stability, whether it be electrical, fluidic, or some sort of mechanical or aerospace project. So determination of eigenvalues, and sometimes their corresponding eigenvectors, though the eigenvalue is really the prized number out of that matrix, is very critical. So to start off with something a little bit fear-inspiring, that is page 180, 181 in Chapter 5. It's actually section 5.6, and it contains 2 full pages that constitute 2 iterations of QR decomposition, which is the iterative method used to find eigenvalues. So it can be pretty involved, but of course once you transfer this into numeric form, it's nowhere near as terrifying. If we can show you real quick the algorithm involved with doing QR factorization, the actual operations take up, what would that be, 18 lines plus the initial function call, because you have total of 27 minus 7, so 20 lines. 20 lines, total 20. So it's not that crazy. I mean, some of these are if statements. It's not a big deal once you actually look into the process QR factorization is doing. But one thing that's interesting, it's a very iterative process. So doing this by hand, no thanks. It'd be much easier to do the determinant method. But now I've started mentioning things that place me ahead of myself. So I'm going to flip back to the beginning of Chapter 5. And we're going to do the walkthrough of the chapter together. So eigenvalues and eigenvectors. We are going to principally cover characteristic equation. I'm not going to teach you the basic power method, the inverse power method, the shifted power method, any of those, because they give you one eigenvalue. Why not use a numeric method that gives you all of them at once? And if you guys really want to go teach yourself basic inverse or shifted power methods, go for it. We're going to spend our time in this special use chapter teaching you the most versatile tool, the tool that gives you all of the eigenvectors at the same time, QR factorization. Of course, MATLAB already has a eigenvalue determination function. We'll cover that at the very end. You've probably already used it in other courses, but now it's important to know the algorithm hidden behind all of this discussion. So put very simply, an eigenvalue, as described in 5.1, is lambda. So if you played Half-Life, you're familiar with that symbology, but it is a single scalar number that satisfies this equality. So you have an entire matrix multiplied by a solution vector, U, and then that is equivalent to the eigenvalue times an eigenvector. So that equality is what you're trying to set up. You view it in a general way, but really the book's just getting down to saying that for solutions of differential equations, you can find the eigenvalue associated with the coefficient matrix to determine the stability of the system and really the speed at which it converges. The eigenvector most oftentimes really is pertinent to the coefficients in front of the system, but really the boundary values trump that. So that's why most of the authority and emphasis is on determining eigenvalues. The characteristic equation of determining eigenvalues is when you take the determinant of the coefficient matrix A minus lambda I. This is probably the way you've seen this taught in a linear algebra course. For small matrices, 2 by 2, 3 by 3, not a big deal, right? You end up with a polynomial, you distribute things out, and you can find the unknown values lambda by finding the roots of that polynomial. In fact, if you can determine that polynomial numerically, you use all the root finding functions we just discussed in Chapter 3 and Chapter 2, maybe a little bit Chapter 2 as well, to find those values. In fact, MATLAB's roots function would be perfect. The hard part is actually distributing an unknown size matrix out with that unknown variable lambda and keeping it somewhat organized in numeric sense. But regardless, the basic power method is a material we are not going to cover. We're going to go straight to discussions. Shifted power method, right here. There we go. QR, factorization, and iteration. QR factorization gets its name because you end up using, well, two matrices called Q and R. More specifically, Q is specifically orthogonal, and R becomes upper triangular. Orthogonal, a highlighted note of merit, is a matrix whose inverse is the same as its transpose. That makes it very easy to find the inverse of that matrix because you just flip around the diagonal. Obviously, not all matrices are that way. These are special case entities. And the point of this is once you go through enough iterations of QR factorization, you end up with this upper triangular matrix form where the bottom left-hand side is completely zero. And the outcome of that circumstance is that your eigenvalues are stacked up along the diagonal, lambda 1 through lambda 4. So to achieve this mythical and magical factorization, I love how they just start talking up here at the top of the page like, oh, well, you just factor it. You just factor it by an orthogonal matrix and an upper triangular matrix, and it just happens. There's a special use matrix called the householder. Yep, I guess I said that right. The householder matrix that is defined down here in equation 538. That is key to performing this factorization, and you'll see it used multiple times. In fact, it's so important that I went ahead and boxed it in the example we'll follow through with. So the process and kind of how we're going to achieve this final solution form down here, A sub n in a upper triangular form. Oops, put it back on the camera. A sub n, upper triangular, is described on page 175. And they go through a rather lengthy example in the following pages. But the best thing to follow, I would encourage you to skip forward to example 5.3, which we'll go through together here. So given the coefficient matrix A, and if you're asked to factor into an orthogonal matrix Q and an upper triangular matrix R, so perform QR factorization on this. Notice it didn't say find the eigenvalues. There's another step after you've successfully factored it to find the eigenvalues. You start by doing QR. So you just follow the process. First determining C. In this case, C is the first column of the matrix, the original matrix here. Then you find the three-element column vector E. This one follows a formula. And it depends on the sign of the, I believe, the diagonal element. So if we go over to the code real quick, in the determination of E, the highlighted region right there, and determination of the E formula for any row J that we're working on. So if the coefficient, if the C vector in location J is greater than 0, then E of that location is 1, otherwise E is negative 1. So there's a bit of logic to apply, but it follows a formulaic example. So again, once you are comfortable with that formula and pattern, you're set. If you want the explicit notation of how to define E, I believe it starts in 550. In fact, the definition probably happens a little bit before. I believe they start discussing it in the upper portions of page 176. So these are all just components you are pre-calculating for creation of the householder matrix, which actually lets you proceed. You need to figure out the 2 norm, the Euclidean norm of the vector C. This is that vector you formed right on the previous page. So all the elements squared times taking the square root of their summation gives a particular magnitude in that case. That's corresponding to the length of the vector C. So then you finally go through and calculate this intermediate term V, nu, whichever way you do it, C plus Euclidean norm multiplied by E. And so finally you have very nearly all the components for the householder matrix. I mean, they do some intermediate steps here and go ahead and pre-calculate V transpose times V and V times V transpose. Notice different solutions. Matrices are not commutative. So now you actually go through and can populate the entirety of the householder matrix, just plugging and chugging. So identity matrix minus 2 divided by V transpose V, multiplied by the product V times V transpose. And that, on the right-hand side, is the outcome of householder. Once you have that, for the initial step, the Q matrix is just equivalent to the householder matrix for the first step only. In the future, on the second iteration, when we're in the same spot, the Q matrix will be equivalent to Q multiplied by H. But for the first step, you're assuming the Q matrix was initialized as the identity matrix. Then the R matrix is, by definition, householder matrix multiplied by your initial coefficient matrix A. So you can see we arrived at this point, though not all of the not all of the elements are 0 in the lower triangular portion. We're looking to have a populated diagonal and a completely upper triangular form, And once we achieve that state, we're done. We're not quite there, so we get to iterate and do this again. So now C, you move on to the second row. But notice the first element will become 0. So C is a bit formulaic as well. The vector E follows the next form, though the middle term of C, so this is C2, so we look at the second term of the C vector, is negative, so E follows the same form with a -1 in the second spot. Again, the 2 norm, Euclidean norm, the length, whatever you want to call it, of the vector C is calculated. You go ahead and pre-calculate what V is going to be equal to, as well as V transpose times V and V times V transpose. You see how this is already following a formula. This terrifies me. I don't want to open a math book and see a page full of matrices multiply by each other, because it's just the eyes glaze over and the mind shuts down. But look, it's the same stuff over and over. And really, they're just breaking this apart into tiny, tiny little steps that make it very easy to follow. Just look at what they're calculating. So 2 norm, that's an easy step. This is just multiplying matrices together and adding them. Not a big deal. This type of multiplication, V transpose times V, done every time. V times V transpose, done every time. You can just program it in. Good to go. Householder matrix, same form every time. Identity minus 2 divided by V transpose times V multiplied by V times V transpose. This would be terrible if you had to do that by hand, but that's the point. This will not be done by hand. This is a numeric method. If you're going to find eigenvalues by hand, you would probably do the factorization method. So, we found H. This matrix right there that I'm pointing at is the H matrix. So you can take Q for an update, multiply the previous Q, so that's Q of 1, multiply by H of 2, gives you Q of 2. That's the new Q matrix. Notice it didn't really change tremendously. Let's compare it over here to the left. So the first column, entirely the same. Second column, a little bit different. Third column, a little bit different. So it's just an update, an iteration. You would expect it to just move a little. So then, of course, the matrix R, which we're trying to get into upper triangular form, is updated this time. And hey, look, it finally is. So R is upper triangular, and that completes the factorization, which means that you have successfully finished QR factorization of the original matrix A. If you multiply Q and R together, you should arrive back at your original coefficient matrix. So that is the first big chunk in the process of finding eigenvalues of a system.